last section. So, preface this section with out of the however many years I've been doing this, I bet I've taught this maybe 3 times, 4 times. Most time we run out of time and I don't get to it. It is a very, very small portion of the AP exam. It is more of a review from chapter 4 than it is a new inference. So if you remember chapter 4, and you don't, I'm sure, that was bivariate data, where you had slopes, y-intercepts, r's, r-squareds, standard deviation, residuals, a lot of stuff about that, okay? I'm going to cover a lot of stuff that's mostly going to be on your homework. It will not be on your test. So I will let you know what's on your test so that you will be prepared for that portion of it. So, inference for slopes. Inference for slopes. Here we go. Inference for slopes linear regression. Scatter plot of the duration of time interval between eruptions of Old Faithful. 263 eruptions for a single month. Okay, so I have all 263 eruptions of Old Faithful 1 month. That is the population, right? That is the population. So here is the population of all 263 eruptions with their duration time, how long they erupted, and their interval units from the time, okay? 263 dots. We found the least squares regression line of that data. Your notes won't go with this hardly at all. I'll tell you for that part too, okay? So when we have the least squares regression line, we have a positive slope, we have a y-intercept, we can find all that stuff about it, right? We'll now start thinking about statistics and how we're using a lot of this information, because this is the population. A lot of times we don't deal with populations, we deal with samples. So out of these 263, let's say I take a random sample of 15 or 30 of those, maybe 20. So if I take a random sample of 20, I'm going to have 20 dots up there. Shh, guys, 20 dots up there. If there's 20 dots up there, it's probably not going to find the exact same slope. It will not find the exact same y-intercept. Okay, with all that stuff, right? We understand that, I think, because of sampling variability. If I did another 20 and another 20 and another 20, I'd have several of these slopes and several of these lines that would mimic the population but not be the exact same as the population, right? So we know that we have a regression line is equal to y hat a plus bx, right? We've done that before. A is the y-intercept, b is the slope. That would be if it was the sample. That would be if it was a sample. That's what we did in chapter 4. We did everything with y hat and we did a plus bx. If by some crazy chance we had this population, they're going to change it to mu sub y, and then they're going to change a to alpha, and they're going to change b to beta. And so we have a population line, we have a sample line. The sample line is y hat a plus bx. This is what we dealt with in chapter 4. This is kind of what we're looking at today, okay? The difference between these two is this is the population. Guys, every time we have Greek letters, it's population, right? Mu is the mean. X bar is the mean of a sample. P hat, that is rho actually, right? Standard deviation, standard. So anytime we have Greek letters, what are we talking about the population? Well, they were talking about the population here. Alpha, beta, A, and B. Just kind of recognize those couple of things. Okay with that? There's a sample. The green line is the line of best fit for that. I think it's 15 points. The y-intercept is 44 and the slope is 10. Here's another set of 15. The y-intercept is 39. The slope is 12.5. Again, the blue line is the population line. If I did it again, I have another y-intercept and another slope, right? And if we did it over and over and over and over again, we'd have a whole bunch of these slopes and a whole bunch of these y-intercepts. This happens to be the sampling distribution for the slopes. Actually, let me rephrase that. It's not the sampling distribution. It's a distribution of samples. Okay, 1,000 of them. The blue line is the population line. Then those green lines are all those different kind of samples that we got with it. We know that they're going to get close to that population line. Sometimes they're not. That one was 10, I think. It's pretty far away from the population slope. I think another one was 12.5, which would be like right here. We would expect to get that one because it's within 2 standard deviations. Again, just kind of soaking all this stuff up. A lot of this stuff is replays from previous units. You don't need to know any of this stuff. But the mean of the sampling distribution of the slope, the mean of the slope is equal to the mean of the population. The standard deviation of the slope is equal to the standard deviation divided by the square root of n with something else attached to it. Don't worry about it. And then the sampling distribution is always going to be approximately normal, provided you have a large enough sample size. We learned all that stuff in chapter 7 about means and proportions, right? We know that the mean of all the x bars equals to the population mean, and the standard deviations over the square root of n. And we learned about p's. Well, now we're just talking about slopes. And again, you don't need to know any of these formulas or anything like that. Picture this. Here's the population line, right? Here is a point. And then I can have all these points that are around it. It's kind of a 3-dimensional shape. So we have all these normal shapes that are kind of going along with it. I think that slide's worse. Here's a condition. You need to know these for homework. You need to know these for homework. I will not ask you any of these conditions on the test. Okay? So the conditions for regression inference is different than all the other conditions. One of them, linear. The data must look linear. The data must look linear. Okay? We know how data looks linear. We're going to look at the scatter plot. We're going to think that it goes in a linear direction, right? We want that data to look linear. Remember, there's 2 ways to do it. One of them is actually looking at the data, which is not always the best. The best way is to look at the residual plot, right? Oh, residual plot. If the residual plot is curved, that means the original set of data was not linear. It was not linear because you have all these positive residuals. Now you have all these negative residuals. Now you have positive residuals. That data was probably curved, right? That would not be a good reason to do linear inference or slope inference. This one would be okay because this data looks linear. This data looks linear. I don't have a residual plot here, but that looks linear. It's okay. That residual plot looks bad. So we want the data to look linear. If it doesn't look linear, guys, we can't do a linear inference with it. We want each point to be independent of the previous point. And that tends to always happen. One point should have no relationship to the other point. Okay, one point should have no relationship to the other point. And we also should check the 10% condition. That goes with, they put that 10% with that independence. Because if the sample is less than 10% of the population, then even if it wasn't completely independent, it will be, because it won't have anything to do with the previous point. So linear and independent points. We want the data to look linear. We want each point to be independent. Okay? Next one, we want the residuals to follow a normal plot or a normal pattern. We want the residuals to follow a normal, make a box plot of the residuals. It could be a box plot, it could be a bar chart, or a dot plot. We just use box plots. I don't like using box plots, but they're the easiest to use, and we'll go ahead and do that. Equal standard deviations. We want all the residuals, we want all the standard deviations of those residuals, the distance. We want them to be somewhat the same. Here, let's just equal standard deviations in the residual plot. These are all scattered about the line, somewhat equidistant. That one they are not. They start off fairly close to the line, but as we get further to the right, they become further away from the line. That one I would not use linear regression with, because all those points are not equidistant from the line. It's not equally scattered. Okay, so the residual plot, the variability of the residuals should be roughly the same. The variability of the residuals. Remember, variability is the standard deviation. We'll kind of go through some examples on these also. Equal standard deviation. This one's good, that one's bad. Okay? And then finally, of course, we need random selection. We need random selection. Okay? L-I-N-E-R. Linear regression. We want the data to look linear. We want each point to be independent. We want all the points to be less than 10% of all of them. We want normality for the residuals. We want equal standard deviations about the line, the distance from the line, all the residuals. Okay? And then randomness. Okay? Randomness. This is the one that they're going to test on your or ask about homework. This one is the one they're going to ask about homework. And this one is about what they're going to ask. But you're just going to get a couple questions on your homework on that. All questions I have seen on the AP test about this have always said conditions have been met. They have all said conditions have been met. So I'm going to go with that again this year. Conditions have been met. So they're not going to actually have you check these conditions. Okay? I want you to understand that they're a little bit different. They're not the same three as all of them. However, the randomness is in there and the 10% is in there. The normality is in there. But we got to have a couple of other things about these. Okay? So don't make it a big deal. Homework. Questions on homework on it. Okay? I will not ask you anything about the conditions on my test. Okay. Let's look at this one really quickly, just so just to make sure you guys can somewhat understand. Miss Barrett's class did a fun experiment using paper helicopters. After making 70 helicopters of the same template, students randomly assigned 14 to 5 drop heights. So we have a drop height, a drop height, a drop height, a drop height, and a drop height. Teams of students released those 70 helicopters in random order and measured the flight time in seconds. So I'm going to drop it from 152 centimeters. This question is real bad because everything's in centimeters, and the next, they're all in inches. So I don't know what happened there. Just going to be aware of that. The class then used computer software to find out the least squares regression line. Here's a scatter plot, residual plot, histogram. They want me to just check the conditions. Well, right now I can't check any conditions without seeing this. So, data looks linear. It looks linear. Each helicopter is independent of the previous one. L-I-N. The residuals look normal. N-E. Equal standard deviations about the line. That looks equal standard deviations about the line. E-R. Each helicopter was randomly assigned. Kind of makes sense? They'll give you those type of things. On the homework, they're going to give you those. They're not going to ask you to plot them or do anything like that. They're just going to give you that and just make sure. Okay? Any questions about those conditions about, again, homework only. Homework only. Nothing on the test. If I did anything on the test, I would say conditions have been met. Don't overreact to minor issues. How normal that needs to look, right? As long as it's close. How linear does that need to look? As long as it's close. How close do those points need to be? As long as it's close. Don't overreact to things that it doesn't fit. Okay, this we've mentioned already. Make sure you do understand that. We use A to estimate alpha. We use A to estimate alpha. We use B to estimate beta. We use B to estimate beta. This we used in chapter 4. This we used in chapter 4. We are turning them into alpha and betas because we're trying to estimate the population. We're trying to estimate the population. You don't need to know that formula, but you need to know that notation. That's the standard error. And when they put the B, it's the standard error of the slope. If they wanted the standard error of the y-intercept, they'll put an A, lowercase. Oh, I can't erase from that. The wrong thing. There. Okay. But we learned even in chapter 4, most of the time the y-intercept means absolutely nothing to us. The y-intercept means nothing to us. Most of the time we're talking about the slope. And so that's why we do inferences for slope. That's why we do inferences for slope. That's the standard error of the slope. You don't care how they get that because they're going to give you that number. They're going to give you that number. You got to know how to read one of these computerized printouts. You got to know that. We did it in chapter 4. Now we got to do it for chapter 12. Regression analysis, flight time versus drop height. Most of the time, they're going to tell you what the x variable and the y variable is. Earlier, Ms. Barrett's class used computer software to perform the least squares regression line of the helicopter. Recall that the 70 paper helicopters from various heights, measured in seconds. Some output of this regression analysis is shown here. We checked the conditions for performing inferences earlier. So this is not the one that's on your paper, but you have one, a computerized printout. You got to know how to read these computerized printouts, okay? You got to know that from chapter 4. So we have flight time versus drop height. Which one is X and which one is Y? Well, I can go over here and see predictor, and I see constant. Remember, we always see constant, and then you see X variable, drop height. So the X variable is the drop height. The Y variable is the flight time. I'm trying to predict how long does a helicopter stay in flight from a certain height. Height is the independent, the dependent is the flight time. Okay, here's that coef. You remember the coef, right? That's the coefficient. So this is the coefficient of a constant, which makes absolutely no sense at all. A coefficient of a constant is just that number. So this is the y-intercept. That is the y-intercept. This is the coefficient of the slope. That is the coefficient of the slope, or that is the slope, I guess, the coefficient of the drop height. So that is the slope, that is the y-intercept. You need to know how to get those two numbers from that computerized printout. Here is S, if you guys can remember from chapter 4. That is the standard deviation of the residuals. That is the standard deviation of the residuals, which 0.16 means that those points are pretty close to that line. There's not a big difference in those residuals. Remember that R squared. Remember R squared. That's the percent of variation in Y, as explained by the least squares regression line of X and Y. You need to know that. Remember, we don't ever use that one for anything. We don't ever use R squared adjusted. Remember, if you want R, you take the square root of that number, right? R tells me the strength, direction of a linear relationship. We got to know all those interpretations. I know, getting close to May, though, we got to start going back to these things. Here they have, looky here. Now, if you guys remember chapter 4, I said, hey, we're going to talk about all this other stuff later. Well, now we're here. Now we got to talk about this other stuff. There's the standard error of the coefficient. That's the standard error of the coefficient. So that's the standard error of the y-intercept. That's the standard error of the slope, because it's just going slope across. Here is the t. That's the test statistic. That is the test statistic. So we're using t's again. We have z's, t's, chi-squares. We're going back to t's. That's the test statistic for the y-intercept. Again, we won't use that. That's the test statistic for the slope. 28. Holy cow, it's huge. Huge. That's the p-value. That's the p-value. So that's the p-value for the y-intercept. Again, we don't use those. That's the p-value for the slope, which again makes sense why that's 0, because that's 28. 28 is a huge, huge number for normal curves. 28 standard deviations away. So what is the estimate for alpha? Well, the estimate for alpha is that slope, or that y-intercept, sorry. Interpret this value. You need to know how to interpret that. When the drop height is 0, the flight time is negative 0.037, which makes absolutely no sense. When you drop it from the ground, the flight time is negative. It makes no sense whatsoever. But that's what it is. What is the estimate for beta? That's the slope, 0.005721. Remember how to interpret that value, 0.00572. Remember, it's over 1. Interpret that. Rise over run. We interpret SLIPE as rise over run. So the flight time, y, flight time goes up 0.00572 for every 1. Again, it goes back, for some reason, it's inches here. It says inches. It should be centimeters. You need to know how to interpret that. You need to know how to interpret that. What is the estimate for sigma? Well, that's 0.16881. That's the average distance away that the points are from the line. That's the average distance of points are away from the line. Give the standard error of the slope. That's SE sub B. Oh, sorry, right here. There's the sorry, I circled the wrong thing. Standard error of the slope. You need to know how to get all that information from this computerized printout. Any question about any one of those points? Okay, that will be on your test. Something like that. Getting the information from a computerized printout. Okay? If you have to go back here, each one of those, right? That's the word and the interpretations. Those are the values and the interpretations. Okay? All right. Confidence intervals for slopes. Confidence intervals for slopes. You know that it's statistic, it's critical value, and it's the standard deviation of the statistic. You already know that. Statistic, well, that's going to be B in this case, because that's the estimate of the population slope, plus or minus. It is a T critical value. Now, please, 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 somebody's going to do this, don't. That T critical value, guys, is not this T. That's the T test statistic. The test statistic is different than the critical value. The test statistic is different than the critical value. The test statistic comes from the statistic minus the parameter over the standard error. That's what the test statistic is. The critical value comes from the confidence level. If it's 95%, then we know what that value is. If it's 90%, we know what that value is. So those are not the same. Please don't confuse that. It's about this time of the year where some students confuse the Z score, the Z critical value, with the Z test statistic. Those are completely different Z's. That's why they put the little star there. That's why that star is there, so you won't try to confuse those. And then the standard deviation of the statistic, well, in this case, that's just the standard error of the slope. That's the standard error of the slope. You need to know how to find the confidence interval from a computerized printout. You need to know how to find the confidence interval from a computerized printout. Here is the big deal. There's your DF. Your DF for this one is N minus 2. That will be on your test. That was on the AP test. That's on the AP test several times. I say several times, once, twice, max. You need to know that the DF is N minus 2 for slopes. DF for means, N minus 1. DF for chi-squared is categories minus 1, unless if it's two-way tables. So you need to know the DF for all different types, okay? This is where it says the values on the computerized regression is not the critical value. It is not the critical value. That is the test statistic. That is different. Everyone knows that cars and trucks lose their value the more they're driven. Can we predict the price of a used F-150? We did this in chapter 4. This was the same data. A random sample of 16 used F-150 Super Crew Cab was selected from among the list of all of them. The number of miles driven and the price in dollars were recorded. There's the 16 used F-150s. Here is the regression data plotted. It looks linear. They're all equidistant, somewhat normal. We'll go with it. Those are the conditions. Here's the computerized printout. That's what I need to see. They are going to ask, what is I think it's 90% confidence interval for the slopes of these trucks. There's my test statistic. Miles driven, negative 0.16292, plus or minus. Then you have to find the T critical value. Coach Mayer's program or inverse T. Coach Mayer program or inverse T. Inverse T, you got to be careful because you don't do inverse T of 0.9. Can't do 0.9 because 0.9 is supposed to be the middle 90%. And if you do inverse T 0.9, you're leaving it short because it's going to include all this. So you have to do inverse T of 0.05 because there's 10 left over, it's half of it. If you use Coach Mayer program, you don't have to worry about it. You just use 0.9. Then N-2 for your degrees of freedom. N-2 for your degrees of freedom. There were 16 trucks, so your degrees of freedom will be 14. And then you're going to multiply that times the 0.0396. There's the B. That's the T critical, the T critical value, 1.76. Not 1.645, 1.645 for Z. It's a little bit bigger than 1.645. And there is that slope error. So this is the confidence interval, and you know that already. We are 90% confident that the interval from here to here captures the true slope of context. You need to know how to write that down. You already do. Make sure we talk about the true slope. Make sure we mention of all. Make sure it doesn't allude to the sample.
There's like no, like, for like the T and the mean stuff, there's like a program we can do, but this would always use it.
There is a program to do it, but you don't need it.
Okay.
because
I mean, it's not real hard to get it.
no. Yeah, I know. No, it's just get it from the computerized printout. Oh, that comes up in one of these other slides. Y'all okay with the confidence interval? Okay, confidence interval. If you really wanted to, you could put all the X values in L1 and all the Y values in L2, but by the time you do that, guys, you're going to run out of time on the test. You're going to run out of time on the test, and the values are already given to you. I mean, it's just going to give you this, which is already on the computerized printout. There's the slope, there's the y-intercept. Only thing it does is it does all the math for you, and it calculates the t for you. But again, you will run out of time on the test. If you find yourself punching a bunch of stuff into your calculator, you're doing something wrong. You're doing something wrong. But your calculator will do a len reg t int. It will. You tell it everything you want it to do, and it will spit it out. When you see a list of data values on the exam question, wait a moment before typing it in your calculator. Read the question through first. Often, I would say more than often, information is provided for you that makes it unnecessary for you to enter the data at all. Very few times will you have to enter the data. The only times I can even think of it is in chapter 10 or 11 where you had to enter that data in your list. That's the only times I've ever seen that you had to enter data, and it wasn't much data. Significance test for the slope. These are really easy because this is the t critical value that they give you, and they give you the p value. So that's already given to you, right? That's already given to you. You know it's the slope. You need to know the ho and the ha. Ho, beta equals 0 most of the time. Most of the time, beta, the slope is 0. We assume, listen to me, there is no relationship. If there's no relationship, then the slope will be 0. We think there's a positive relationship, or we might think that there's a negative relationship. So if we think there's a positive relationship, then the slope will be positive. If we think there's a negative relationship, the slope will be negative. We might think there is a relationship. We might think there is a relationship. We assume there's no relationship. We might think there is a relationship, or we might think it's positive, or we might think it's negative. So you need to know that. And then, of course, guys, you got to tell me what B is. B is the true slope of miles driven versus the price of a new or price of a used truck. Okay, so that you need to know. That you need to know. Because that's the number that's going to go here. That's the parameter. That's the population. The statistic's going to come from the sample. And then the standard deviation of the statistic is SC sub B, which they give you in the computerized printout. Remember N minus 2 for DF when you're turning it into the p-value. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Children development researchers explore the relationship between crying infants 4 to 10 years and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. That's sad. That's mean. Oh well. Researchers recorded the crying measures. So here's the cry count. Here's their IQ. Right? Here is the regression line. Here's the residuals. That's the normality. So my conditions are all met. We got a random sample, yada, 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 yada. Here is the computerized printout. Do these data provide convincing evidence? That means that I should be doing a full-blown process. Again, they will probably say conditions have been met. Here is the T critical value, 3.07. This is the p-value. Listen to me. That is the p-value for a two-sided test. That is the p-value for a two-sided test. They want to know if there's a positive linear relationship. Ho, beta equals 0. Ha, beta is greater than 0. Beta is the true slope of count of crying peaks versus IQ at the age of 3. Right? You got to make sure you tell me what the beta is. You got to know what that is, right? This is the p-value if it was two-tailed. If it was two-tailed. This is the one-tailed test, so that number has been doubled. So you want the p-value to be 0.002. Your p-value will be 0.002. It would make a difference on this one. You're going to reject it either way. But you need to know that the p-value will be 0.002 because that's always a two-tailed test. Beta equals 0. Beta is greater than 0. Beta is the true slope of the regression. IQ score to the count. We're going to use alpha 0.05. There's the T critical value. We don't really have to do anything because it was given to me. There's the p-value, 0.002. Because the p is low, the ho must go. We got to reject it. We're going to reject the null hypotheses. We're going to reject the null hypotheses. There is enough evidence to suggest there is a positive linear relationship between count of crying and their IQ age 3. There is convincing evidence of a positive linear relationship between the count of crying peaks and IQ score. Make sure it doesn't allude to this sample. Make sure it alludes to all population.
On the paper, when we have to do like the full test,
Yeah.
but it says the conditions are met.
Yep.
We just write conditions are met.
You don't have to do anything, but yeah. Yep. You can say conditions check, or you don't have to do anything. Good question. Everybody else okay? I'm not giving you one of these on your open response is going to be chi-squareds. There's going to be 2 chi-squareds. 2 chi-squareds. Okay, hopefully you can check those conditions. Again, those conditions are only going to be on your homework tonight. You won't see those anywhere else. Interpret the values of beta, B. Interpret the values of beta, B, alpha, A. You need to know how to interpret those values. Construct and interpret a confidence interval. Perform a significance test. You should be able to do all of those. Hopefully your homework will allow you to give you a little bit to this. That's all we need for this lesson. Your homework should be posted. It should be posted. Discard.